Okay, so now today we're going to visit a problem regarding the application of Fourier's law in heat transfer for a special case. That is when a problem is in one dimension, that is one dimensional. It is in steady state and heat transfer occurs with no heat generation. We know that the temperature distribution would be linear, and we are going to prove this and make a link between the physical understanding of the problem and the mathematical relations. First, we're going to use energy balance to assume the heat conduction equation, and we're going to simplify the terms regarding this problem, this particular problem at hand, and result into the temperature distribution, which we know is linear. And we apply this into so many problems. But what's the proof? We're going to do the proof here. So about the energy balance, we know that diffusion terms and conductivity terms plus some viscous dissipation and heat generation terms should be in balance. So we can write down the energy equation like this. That is the material differentiation here, the conduction term, viscous dissipation, and heat generation. So in this problem, we got no heat generation, so we can neglect the term Q dot here. And mu times phi would be negligible since the velocity gradients are negligible here, or the viscosity is low, so this term cancels out as well. So we have simplified the equation at hand to a simple Laplace equation like this, that is del squared of t plus, we said that heat generation would cancel out, that is the general form of Laplace equation for a field, that is temperature here, that is del squared t equals to 0. So we have this problem in one dimension, that is only, let's say, for example, x coordinate would be present in this problem. That is a wall, think it as a wall with a width of L. Two sides would be in the temperatures of TL1 and TN2. So these are our boundary conditions here. When we want to expand the del or nabla operator here, we would write down round on round of x. Let's say that k can and may be a variable of x here. It's independent. It's not an independent. It would be a function of x. So it can appear inside the differentiation. So we can write down round on round of x of this whole term here, that is Fourier's law. We know this, that's a constitutional law. There is no mathematical proof of it. It's only comes from experiments. So this term is only appears due to the del squared of temperature in one dimension, and all other terms cancel out. So we know this equals to 0. You see, k is a constant here, so I can cancel that out as well. And I can write down round squared of t on round of x squared equals to 0. Since there is no other variables other than x, there are no y and z present, I can take the full differentiation form, that is round appears as d, as full d, that is d squared of t on dx squared is 0. We know that when differentiation of a function would be 0, the second derivative of it, it is a line, and we can apply the boundary conditions that were t1 and t2 on L. We know that t is equal to, let's say, ax plus b, that a and b are unknowns here, that's a function. We know that this form of a function appears as a line. So this is the main reason that when a problem is in one dimension, that is in a steady state, so we can neglect the whole material derivative term. There is no round on round t, nothing changes with time. And there are no heat generations. You see Q dot is 0 as well. The temperature distribution appears as a line. So this is why we can write down Q equals to delta T on L. See, this is the main reason dt, that is in differentiation form, can appear as an algebraic differentiation, such as delta T, big delta T, capital delta. So we now know that we know from heart that temperature distribution is a line inside a wall with no heat generation, that is in steady state, but this is the mathematical proof behind it. We started from energy balance here, cancel out the terms, simplify the heat conduction equation, then expand the operator of del squared, and we got to the final equation here, that is the second derivative of temperature field is 0. And we solve this ODE, that is an ordinary differential equation. We get to that T would be equal to some constants A and B of AX plus B, and we apply two boundary conditions. At X equals 0, temperature is T1. At X equals L, that is the other side of the wall, T would be equal to T2, and T2 minus T1 would be our delta T. This shows the linear distribution of temperature for this specific problem.